let's continue, okay? So if A is an invertible matrix, K is a positive integer, and C is not 0, okay, then A inverse, AK, CA, and AT are invertible, and the following are true, okay? So A inverse, so if you inverse A twice, you will go back to itself. I mean, this is easy, I mean, according to the inverse, like definition of the inverse, okay? And A to the power of K inverse, it's going to be A inverse, blah, blah, A inverse to the power of K. Okay, this will be a set. Okay, you can take a look. I mean, this one, actually the proof will need induction. Okay, the proof of this require induction because like this is like for arbitrary value K. Okay, so for case 2, this is obviously like the base case. Okay, and you can do it like for like you know, I mean, do the induction steps. Okay, you know, so C A parenthesis -1 is C -1, A to the power of -1. Okay, so this is you can verify this easily. Okay, and A to the power A transpose -1 is equal to A inverse transpose. Again, you can verify this like you know, once you yeah, let me just prove that in the last one. So we want to prove A transpose inverse equal to A inverse transpose. Okay. So first, A transpose inverse. Okay. So according to the definition, okay, that means A transpose times is A transpose inverse equal to I, right? Right? According to the definition, right? And let's see, like this will be the same as this one. Okay. A inverse transpose. Okay. So we do the A inverse. And then transpose. I, okay, equal to this I transpose. I equal to I transpose, right? Like we know I and I transpose basically the same. I is symmetric, right? Okay, so I equal to I transpose, and equal to A inverse transpose, right? Okay, so according to the definition of the transpose, if you remember, so AB transpose equal to what? B transpose times A transpose, remember? Right? In the transpose, there's a property like that, right? Like that. So we applied it here. So it's going to be A inverse transpose times A transpose, right? Right? So it means like, you know, A transpose multiplied with this one equal to I, right? Right? So this one is like AT according to the definition, right? Because this one multiplied A transpose is equal to I. Right? the other, please check by yourself. Okay. So if A and B are invertible matrices of size, and then AB is invertible, and the AB inverse equal to B inverse times A inverse. That's easy because you just multiply AB with B inverse, A inverse. What you get is identity, right? Because we know the multiplication has associative role. So you can do B inverse first, which give you an identity, and then you A inverse give you I. Obviously the other sides also work. So AB inverse equal to B inverse A inverse. Okay. So the inverse of the matrix product. So find the AB inverse for the matrices. This one. If we know A inverse is like that, B inverse is like that. We already give you that. So then the AB inverse will be B inverse times A inverse. So it's going to be this one times this one. Okay. I know it's a lot of calculations, but you get the idea. Okay. Because of time constraint, I think I will skip the calculations, but you get the idea. Okay. And then we can talk about cancellation property. Previously, okay, if there's no given criteria, then as I said earlier, this cancellation does not work for a general case. But okay, if C is an invertible matrix, then the following property holds. If A is equal to BC, then A equal to B. If CA equal to CB, then A equal to B. The cancellation works now. Why? Because if C is the inverse, C is an invertible matrix, that means its inverse exists, right? So say C inverse. Okay. So if AC equal to BC, then you multiply both sides with negative C, so C inverse. So it's A times C times C inverse equal to B times C times C inverse. So originally it looks like this. But because of associative role, so you can do this part first. So that will end up, this will become I, this will become I, and then A. So this is the, under the assumption that C inverse exists. In our words, C is an invertible matrix, or C is non-single. Okay? So the other obvious, CA equals CB, then A equals B. The other also works because you can multiply both sides by the inverse of C on the left hand side. Okay, so basically both sides cases cancellation rules. And then once we know that, okay, if A is an invertible matrix, then the system of linear equations AX equal to B has a unique solution given by X equal to A inverse times B. Okay, so originally we deal with linear system linear equation by using Gaussian elimination or Gaussian-Jordan elimination. But now, okay, with the knowledge of matrix manipulation, we are able to use A inverse, okay, to directly obtain a solution. Of course, you may argue A inverse is not any easier to obtain. But later on, we will talk about how we can, systematically obtain A inverse. Okay, I'm not saying that it's easy to calculate manually, but it's easy to calculate by computer. Okay, but let's do it. We will talk about that. in this example, solve the following system. You can see we have three questions, three set of questions. Okay, but if you look closer, you will see these three systems of linear equation, they share the same coefficient, right? Their A are the same. The only difference is that their B, right? So in other words, okay, if you write it, into like 2, 3, 2. The B I mean, it's different. I mean, for these three questions, but nevertheless, okay, the concept remains the same. So this is your A, right? If you are able to obtain the A inverse, then your solution will just be A inverse multiplied by your B, right? In these three set of equations, of course, the B will be the vector B will be slightly different, but you get idea. You know, it's you can solve these three set of three system of linear equation by just calculating A inverse, and then you get like the solution very quick. Okay, I will not go into the detail like how to calculate like A inverse for these matrices, but you know, as long as like this inverse exists, then the solution for each of these system linear equation is unique. So an n by n matrix is called an elementary matrix. Okay. If it can be obtained from identity matrix IN by a single elementary row operation. So which one of them are elementary matrices? A is A elementary matrix. It is, because we just multiply the second row by 3, right? Multiply a row by a non-zero constant is an elementary row operation, right? So this one, from identity matrix, we just multiply the second row by 3. So this is an elementary matrix, right? How about this one? B is not. Okay, even though it looks like it's good, but remember here, okay, elementary matrix has to be square matrix. It has to be a square, and you have to somehow convert it from identity matrix. Identity matrix also square, right? So this is not even square. How about the C? The C. C is square, right? But the elementary row operation does not include multiplying the row by 0. Okay, so this one obviously multiply the third row by 0. The multiplying one row by 0 is not allowed in elementary row operation. So this one, C is not. D is, okay, it's a square matrix, and also basically we just swap the second and the third row. Okay, this swapping is elementary row operation. And by the way, we only allow one single elementary row operation. Okay, so both A and D can be obtained from identity matrix by one single row elementary row operation. Okay, E. E. How about E? It's a square matrix, and we can multiply the first row by 2 and add to the second row, right? This is a single elementary row operation. Okay, so E is also elementary matrix. Okay, how about F? F is not. Why? Because here we need to multiply the second row by 2, and we multiply the third row by -1. But this will require 2 consecutive elementary row operations, right? And we only allow 1. So this is not an elementary matrix. So the answer will be A, E, and E. Okay, the other 3 are not. Why do we need to talk about elementary matrices? Because, okay, eventually, okay, we can represent our elementary row operations, or like Gaussian-Jordan elimination, by multiplication of those elementary matrices. Okay, so that is the elementary matrix obtained by performing an elementary row operation of IM. If the same elementary row operation is performed on the n times n matrix A, then the resulting matrix is given by the product EA, not EA sports, by the way. 你听懂这个？听不懂就算了。Okay, EA. So if multiplied elementary matrix to your matrix is equivalent to you perform a single elementary row operation on matrix A. That's very interesting. Okay, so multiplication of matrices is not commutative. This is like I just want you to know EA is different from AE. Okay, EA is different from AE. Okay, so let's take a look. First, for example, the first, this is E, the left-hand side. This one is E. This one is a arbitrary matrix A. Okay, so this one is a elementary matrix, right? Why? Because we just swap like the first row with the second row in identity matrix, right? That's an elementary matrix. And then if you multiply this one with this arbitrary matrix A, all you're going to get is this one. And this one happens to be you are swapping the first row with the second row, right? Right? Okay, so swapping 2 rows is one of the elementary row operations, right? So how about the second one? Second one is you multiply the first row by 2, right? This is again one of the elementary row operations. And if you multiply this elementary matrix with an arbitrary matrix, okay, what you are going to get is the resulting matrix is you are performing elementary row operation for the first row. You multiply the first row by 2. The third one, okay, is again an elementary matrix because you can obtain this one from identity matrix by multiplying the first row by -2 and then add to the third row, right? If you multiply this elementary matrix to arbitrary matrix A, what happens is that it's going to be the same as you are multiply the first row by -2 and add to the third row. You can check it out by yourself. So this is important because, okay, all these elementary row operations now become matrix multiplications. Okay? So, and also, these elementary matrices obviously are invertible, right? For example, okay, you swap the first row with the second row. You can swap it again to get like an identity matrix, right? Okay, and if you multiply the first row by 2, you can obviously do the inverse, like multiply the first row by 1/2, and to get like an identity matrix. If you multiply the first row by -2 and add to the third row, you can reverse the effect by multiply the first row by 2 and add to the third row, right? You can see that when you multiply these two, you get an identity matrix. So all these elementary matrices are invertible. I mean, either you can understand it like that, or another way to understand this is all these operations are invertible. All these corresponding elementary row operations can be undone by elementary row operation. Okay?对，今天好像讲中文讲一下什么？你们都 OK 吗？有些同学眉头比较没深锁，不知道是对啊，那个，如果你觉得我英文真的有一些问题哦，有可能是我英文讲不好，有可能，那不一定是你听力问题，毕竟不是老美，对不对？所以如果你们觉得我英文有一些听不太懂，没有关系哦，就是举手，举手并不代表说你英文不好，也可能我讲不好，那我很乐意再重讲一次，那可能用英文重讲，或用中文重讲，对，这样也很好。我跟大家有讲过，用英文教课的原因，其实是让我自己练习，其实我是很自私的，对，所以说也是希望说如果你愿意让我有多机会练习，那也很好，对不对？所以说你有问题多举手，好不好？对。Now, anyway, let's continue. So, this is an exercise. Find a sequence of elementary matrices that can be used to write a matrix A in row echelon form. So this has become more and more interesting. Okay. So from A, okay, probably we don't have much time. So let's just look at this from here. Okay, we know like we can do a swap because first we need to have like the leading coefficient of the first row. Okay, the first element of the first row has to be non-zero, so we swap like the first row with the second row. And then we try to multiply the first row by -2 and add to the third row. Okay, so we got this. And then well, the second row is good. So nothing to be done. So the third row, okay, we can multiply the third row by 1/2 to make it like this. So that's it, okay? Because it only asks us to convert it into row echelon form, right? So this is already a row echelon form. Okay, so let's have a look. So from left-hand side to right-hand side, this one, it requires a swap of the first row and second row. So the corresponding elementary matrix looks like this, right? And then from the second one to the third one, basically we multiply the first row by -2 and add to the third row. So the corresponding elementary matrix looks like this. Okay. And the third one, okay, we need to multiply the third row by 1/2. So the corresponding elementary matrix look like this. So, in order to obtain like a row echelon form like this, we basically from our original matrix, we multiply this one first, and then this one, and then this one. Okay, so this is, if you know this one as E1, E2, and E3, then it's, you multiply this one. On the left-hand side, E1 first, and then E2, and then E3. And you are going to get your row echelon form. If you know, I mean, if you notice, actually you can continue this process to obtain Gaussian Jordan elimination. Obviously, right? By using like elementary row operations. Right? I mean, it's just like we just stop the row echelon. Okay? So that A and B be n times n matrices. B is row equivalent to A if there exists a finite number of elementary matrices E1, E2, blah, blah, EK, such that B equal to E1, E2, blah, blah, to EK. This elementary matrix multiplied with A. So this pretty much means that we can use the elementary row operations to obtain B from A basically. Okay, and the square matrix A is invertible if and only it can be written as the product elementary matrix. Now we can somehow convert A into identity matrix with a number of elementary row operations that are represented by E1, E2, EK. So if A times if this EK minus 1 blah blah to E1 times A equal to I, then obviously A inverse can be represented by this one, right? This of the element elementary matrix will become A inverse because this thing multiplied A is I. In our world, okay, A can be written as E1 inverse times E2 inverse blah blah times EK inverse, right? Yeah, I think like this is an example, but I think I'm running out of time, so I will just keep that legalized. Okay, so from A to all the way, by using the elementary row operations, we obtain like the identity matrix. So the corresponding elementary row operations, there like the elementary matrix are here. So now what? We multiply the original matrix with this elementary matrix, we can get like the identity matrix. And the inverse will be the inverse of this one times the inverse of this one. Blah, blah, blah. Okay, so you get identity. I'm sorry, A inverse is this, and then the A equals the inverse of this. Okay. So, yeah, I think I'm running out of time. So, in case n times n matrix, then the following statements are equivalent. First, A is invertible. AX equal to B has a unique solution for every n times 1 column matrix B. Okay. And AX equal to 0. X equal to, so now this is like a homogeneous system linear equations, okay, has only the trivial solution.